In this lecture, we have sent a transaction to our smart contract through the truffle console, and we have also specified a value in the transaction, which means we are sending some ether in the transaction. We have specified 10 ether, the value in a way. We have sent the transaction, we have received it in the smart contract, it was processed in the block, so it was added in the block, therefore the changes were applied to the state, and now we have on the smart contract 10 ether. In this lecture, I would like to take a look on more details about the blocks, about the transactions, and I would like to talk, I would like to give you some more information. So this lecture will be AI lecture, so additional information. Okay, let's start and let's clear out some things here. So let's take a look at the ganache, and you know that our transaction was sent to the network, and the state change was applied when the block was added into blockchain. So you can see here, the first block, when you have created a blockchain ganache, when you have initialized, was added automatically. That's a genesis block. And all of the other blocks was added after that are linked with each other. Every block is linked with each other. So when you will inspect here hash, block hash, you can see here this hash. Block hash 14741. When you will go to block 1, you can find here parent hash. Actually, it doesn't say here, but I will show you in the console that this block contains parent hash that links to the previous hash. So when you will change some block in the blockchain, all of the other blocks after that will be invalid, basically. All right, so let's take a look on the blocks in more details in our console. Okay, let's stay here in the development in a console terminal. Yeah, and let's write here one command. We will be getting the blocks here. Okay, I wish I could make here some more space for you. Oops. And let's get a block number. Okay, so let's write here web3 etH, and let's call here a function get block, and it will specify the number of the block you would like to get. Okay, so we can specify either from the 0 to 9. So I will get here my last block, 9. And I will get here information about the block. So you can see here hash, parent hash, mix hash, nonce, SHA-3 a log blooms, transactions root, a state root, and so on. All these informations about the block when it was added into the blockchain. Let's get the block number 8, and I will show you. And I will compare here this parent hash here. This parent hash will be hash of the previous block of this here. Okay, so 24777. And you can see here parent hash here is a 24777. So this means that the blocks are linked to each other. So the new block points to the previous one, and this previous one here points also to the previous one. This one here, this parent hash will be hash of the block 7. Okay? Then you have here our mix hash and the nonce. These two parameters are very important because thanks to these parameters, the block is added into the blockchain. So you can imagine, I will maybe draw it for you. Okay, if this will be open if this will be open, that when you are sending transactions, and actually better would be to show you something else. Let's go to browsers. Let's open here a new tab, and let's search here for Ethereum Network Live. Ethereum Network Live view, maybe. This one here. How you can visualize Ethereum network. You can see these transactions are transactions in the mempool, and they are added lots of transactions every second. That's a transaction to send the ether, that's a transaction to call smart contracts, and so on. And you can see as soon as there is a miner, there is a node in the blockchain network, they will get the transactions, they will order them, and they will add a block into the blockchain. And when the block is added into the blockchain, then the transaction is considered to be accepted, and the state is changed in the Ethereum. So here you have it. You can that's how you can visualize it. And on the ether scan, you can see the blocks that are added here, and you can see they are containing a transaction. Okay, and when the block is added, then, as I mentioned, then the state is applied. It's applied for when you are calling the smart contract, when you are sending just the ether from account to account. That applies for anything on the network. When you want to do changes, you need to send a transaction, and the transaction has to be added into the block, and the miner is responsible for mining these blocks. So you can imagine you have here different types of miner. You can see this miner, this miner, this miner, this miner here, this miner, and they are competing with each other basically. Okay. So you have this network of competing miners, and the winning miner will add the block into the blockchain. Okay, I hope this will stop loading soon, and I will show you a diagram. Okay. Okay, perfect. Okay, and new empty node landscape, perfect. Okay, so you have these competing miners, right? You have Ethereum network, and you have these competing miners, and they are competing whoever will add a new block into the blockchain. Okay, and they are just the nodes in the Ethereum network. They are getting a transaction from the mempool. Each of them have access to the mempool, of course. Okay, all of them have a transaction in the mempool, and they are trying to create the blocks and add it to the existing blockchain. Okay, they are competing against each other basically to form this block and to add it into the block as a new block into the blockchain. In order to add this block into the blockchain, they are running algorithm. Okay, they are getting their transactions into the block. So they are ordering the transactions. They are running them through the algorithm. So all the informations from the potential block are put into the algorithm, and all this information together with a special number, nonce number, it has to be larger than some target. That's the basic of the algorithm. Okay, there is much more detail into it, but they are looking for this nonce number. Okay, this nonce number has to be larger than the target, and there is no better way to find this nonce number than just basically just run the algorithm and always try to increment number. So basically nonce plus 1, and comparing the target. If it's bigger than the target, then you can add a block into the blockchain. If you are first, you can add it there. Okay, and then basically this is running in the while loop, and you are incrementing nonce. If the nonce is bigger than the target, then the miner can add this block into the blockchain. Okay, and every blockchain is unique. It's a unique information because it is a different transaction always, and also some other information from the block are computed into the hash, and the hash plus this nonce, and also other information. If they are bigger than the target, then this can be added into the blockchain. I will not go into much bigger details here into this because that's really out of the scope of this course, but that's just the basics, what you should know. The blocks have a nonce, and if the nonce is found and it's bigger than the target, then the block is considered to be found, and you can add it to the block. Basically, this work here, what you see here to find the nonce is called proof of work. Proof of work. POV, proof of work, you will heard about a lot. Proof of work, this means the miner has to do some work, he has to run some algorithm, has to use his computational power of his computer to spend some money to mine the block, and as the reward the miner will get from the network, he will get some Ethereum, some ether as the reward. Okay, so there's a proof of work algorithm. So miner has to do some work in order to add the new blocks of the transactions into the blockchain, and each block is pointing to the previous one. Okay, so now let's take a look what algorithms they are running, these miners. This algorithm is called etHash. Ethereum. Okay. You can get here the entire algorithm, how this is computed. You can see why I didn't want to talk here about this in the details, because it's quite complicated. You can imagine this would be for entire one course just by itself. What we will take a look here is the miner part, this mining part of the algorithm here, and you can see here basically what the miners are looking for is this nonce. This nonce, basically they're looking for a random number from interval of 0 to 2 on the power of 64. And they're in the while loop, they are they are putting it with the other informations about the block with the data set and the header, the nonce, and it has to be bigger than the target. If it's not, just simply increment nonce plus 1 and run this algorithm again until you will find the correct number, which will be larger than the target. If you have a nonce, then you can add the block into blockchain. So yeah, that's basically it. So random integer from 0 to 2 to the power 64, and yeah, then just increment by 1. And here is a modulo operator, so you are running it. You will not go over limit, basically. Okay, I can show you an example of it. So we have a basic idea. You can consider this lecture done already. This is just a bonus information. So if you want, you can skip to the next lecture. Okay, so let me find this here. So basically what we are looking for, if it will allow me to write, because it's still loading. Okay, let me see. Okay, so here I have some space. So let's say we are looking for a nonce number. A nonce can be from interval of 0, not to 2 to the power 64, that will be too big. Let's say 2 to the power of 3. So we are basically looking for interval 2 to 8 for a nonce. First, we will choose the randomly nonce from this interval. Right, so let's say we will start with the number 6. We'll find the 6 and we'll verify if it's bigger than some target. Okay, that target is not important right now. I just want to show you incrementation part. Let's say the 6 is not bigger than the target. So what we'll do, we will run it through the 6. We'll add 6 plus 1. And we'll use here a modulo operator, and we'll get here modulo operator was saying on the 2 to the power of 64. In this case, the maximum here is 2 to the power of 3. So modulo of 2 to the power of 3, which is 8. Okay, so 6 plus 1 is 7, modulo 8 is 7. Okay, so that means that the nonce will be 7. Okay, I'll run it through the algorithm again. So now the nonce is 7, so we'll go to the next step. So now 7 is bigger than the target. Again, 7 plus 1, modulo 8. Okay, and the modulo is just a reminder after division, okay? So 7 divided by 8, it's basically 7, because 8 doesn't fit into the 7, so you will get this reminder of 7. But here 7 plus 1 is 8. This 8 modulo 8 divided by 8 is 0. So your new nonce is 0. Okay, so new nonce is 0. So you are going to while loop, and you now have a 0 is bigger than the target, and you are basically starting over. So now 0 plus 1 modulo 8 is equal 1. So your new nonce is 1. So now you're starting with the 1. So 1 is bigger than the target. Okay. So now you understand this modulo operator, right? So we have chosen randomly 6 from this interval. So we have started with the 6. Then thanks to the modulo, then we are incrementing here to a 7. And now thanks to the modulo, we are not going into 8. Okay, but we are going straight to the 0. And then we are setting over 1, 2, and so on. Okay, so since the interval is 0 to the 8, and if we wouldn't have this modulo operator, we would be incrementing, and we would go over above the limit. We would go eventually without this modulo to 8. Then we will go to 8, then we would go to the 9, 10, and so on. That's outside of the interval of the numbers. So, of course, then we would provide the wrong values. But guys, you don't need to understand these details. That's really not necessary. But I just want to show you how that this is not something really magical, but that's a real algorithm here that's running, that's looking for this nonce number and feeding it into some other code. Okay, so that's the etHash algorithm. And what else here? I will see the other details. No, what is important is the hash, parent hash, and this is nonce number. By the way, this nonce number is 8-byte number, so this means that 30 to 64-bit. So there's 8 bytes. If you will copy it and you will paste it here, you will see this is the 8-byte number. 16 selected, so this means 8 bytes a number. Okay, so I can write here some comments for you, so you have information about the block info. Okay, let's write here nonce. Nonce. Let's write here a hash that when combined with the min hash proves that the new line proves that the block went or block has gone through proof of work POV. Okay, so that's basically this nonce number, and the nonce number has 8 bytes, which is equal to 64 bits number. That's the number you could see 2 on the power of 64. That's this number. Okay, so nonce hash, or we can just basically say the number that then combined with the min hash proves that the block has gone through the proof of work. And as you can see here in these informations, a nonce and the min hash is 0 because we don't basically need to do any proof of work. We are just running simulation on our private network, on our private computer. So we don't need to do here any work here. We just automatically consider a block to be valid. And of course, that's not how does it work on the real network. There are the real miners that they are running the algorithm, and they are competing with each other to find the block faster. Okay, about these other informations, we'll be talking about them later. These details, guys, are more for the separate cores. I will see how much details we'll be talking about. I would like to focus in the further lecture, in the future lectures, more on the programming side, and I would like to create some cool applications. But yeah, we still need to explain some details, so don't worry about that. That's gonna be it, guys, and I hope to see you in the next one. Cheers.